Greetings once again. If you have noticed last time, we talked about inequalities. I think that was supposed to be Friday. We talked about inequalities. And let me just do a quick summary of what we did. And then we said, if let's say you want to solve some inequalities, the first step was you bring everything to the left hand side of the equal sign, of the inequality sign. Let me write this of the inequality. Let me just have a sign there. And then after you have taken everything to one side, the next step we said you want to find the critical values. And then finding the critical values is simple. We first gonna change the inequality sign to equality sign. That was the first thing that we said we need to do. And then secondly, we find the set of find the set of all the values x such that the equation is equal to 0. So what we basically mean by that is that after you've changed this the inequality sign to an equality sign, you are actually solving for x, or if there is a numerator in the denominator, you're looking for the values of x that actually make the numerator equal to 0. And then secondly, you want to find the set of all values x that make the equation undefined. So there are two things that we are looking for here to find the critical values: the set of values that make the equation undefined, and the set of values that actually make it equal to a 0. And then the next step is, once you find your critical values, you want to draw the number line. And then this is gonna be your number line. And then once you draw your number line, you're gonna mark the critical values there. Just write your critical values there, and then you have some holes there. Right, now that you have this, if you have less than or equal to, all the critical values that actually make the equation undefined, you shade them. But the critical values that actually make the equation undefined, you always don't shade them, even if you have this sign there. And also, if you have this sign, inequality sign, you do the same thing. But but if you have this sign or that sign, you don't shade at all. And then, as we said, you mark the critical values in the number line. You mark them in the number line, and then after that, you pick a region. If let's say you have in this number line, you want to pick a value here, and then you plug it to the given inequality and see if you are getting a positive or a minus sign. You pick another value here, you pick another value there, you pick another value there, and then you check the sign. That's the meaning of picking a value in its region. You pick a value in each given region, right, to check the sign. Right, is it a plus or is it a minus? Now, after you have done that, you can see that if the desired region is here or there or there or there, all you need to do, you just draw the arrows and the line segments joining the regions that you actually looking for. So the next thing is you choose the regions, and then you have your arrows and your number lines, and then you can finalize your answer. And then we said that you're gonna end up with something of this sort, and then you either have this, and then let's say you have something of this kind, and then you have that. So you have that. What we said we don't really want to do, if let's say you have a quadratic and now it has two critical values, we said that you can either have a nice shape of this kind, but when you are using a shape, there are two things you have to be careful of. First of all, if you have this sign or that sign, you know that where there is a critical value here, you're supposed to shade. So we must see the shade. You must see a shade. But if let's say you have this or that, we just want to have a number line of this sort, but you must see that there is a hole there, right? And the next thing that we want to see is that if the region you are looking for is in between here, we want to see you shading that we are looking for this region, so that you don't end up losing the marks. But if you are not sure of the shape of that quadratic equation, I always say go for this kind of a number line. Of course, usually theory and summary doesn't make sense if there is no example. Let's take one example and actually move to the business of the day, which is the functions. So suppose I give you an example of, and I say find the value of x, or I can say solve for x, or solve the inequality. And this inequality is gonna be of this type. Let's say 2x squared minus 5x plus a 6, and then all divided by x minus a 3, and we say that this is less than or equal to a 0. Now, how can this be actually determined? First of all, we said that the first step is to bring everything to one side. You can see here we already have a 0, so everything is on the left, so there is nothing else that we need to do. We just need to move to the next step, which is find the critical values. Find the critical values. Now, if let's say you want to find or you want to solve inequality, you need to make sure that you get rid of that idea of I want to cross multiply. We are not cross multiplying anything here. And that idea of I want to factorize this and cancel if there is a common factor in the numerator and the denominator, we are not canceling anything here. All we are actually doing here, we want to solve this inequality. So that idea of canceling things, cross multiplying, get rid of that mindset. Just get rid of it now, because you will be able to make a lot of mistakes. I know that some people will tell you that factorize, cancel out, and then on the other side specify that this cannot happen. But the best way to deal with this, don't cancel anything, and also don't cross multiply. Now, the first thing is we wanted to change the equality to inequality. So we're gonna have x cubed minus 2x squared minus 5x plus 6, and this thing all over x minus 3 is equal to 0. So we want to find the critical values that are actually satisfying this nice equation. Now, first of all, we said that for this thing to be equal to a 0, it's only the numerator that can actually contribute to that. Once the denominator is equal to 0, we'll get an undefined. So we don't want to have that scenario. So x minus 3 equal to 0 is also one of the things that can actually contribute to the critical values. Now, first of all, we said that we wanted the numerator equal to 0, right? We want the values of x that make this equal to 0. In other words, the numerator equal to is 0. So we wanted to have x cubed minus 2x squared minus 5x plus a 6 equal to 0. Now, if you have this nice thing here, how can we solve for this? This is a cubic. Is there any common factor here? Because first thing that you want to do when you're solving an equality, equality or solving for x, you want to make sure that if possible factorize. When you factorize, things will be easy. So how do we factorize this? We look for the factors of 6, right, and then we deal with that. But if let's say you don't know what to do, first look out for the common factor. The highest common factor here that we have is just a 1, so pulling it out is not going to help. So the greatest common factor factorization is not going to work. And now we move to the next step. The second method of factorization that we did, it was splitting of the middle term method. But we said that the splitting of the middle term factorization method only works if you have 3 terms. Yes, we tried to force it to have to factorize if we had 2 terms when we had a difference of 2 squares, but in this case we have 4, so we cannot use the splitting of the middle term method. Now we move to the other. Remember that if the splitting of the middle term method is not working, completing the square is not going to work, because the splitting of the middle term is more powerful than the completing the square, so the completing the square is underneath. So now we need to move to the other 3. So we had factorization by inspection, we had synthetic division. Factorization by inspection is the same as trial and error method or the K method, and then the second one was synthetic division or the long division. Now what we will use here, we're gonna use synthetic division because it's shorter compared to inspection. How does it work? First, you look out for the factors of this. Remember that this is positive 6, so the factors of positive 6 is gonna be plus or minus 1, plus or minus 2, plus or minus 3. Plus and minus 4 does not go to 6, so we jump it. Plus or minus 5 doesn't go to 6, so we jump it. So we end up having plus or minus 6. Now we're gonna check each of these factors that is actually making this equation equal to 0. Now if I am plugging, let's say I'm plugging a 1 there, I will have 1 cube and then minus 2, 1 squared, and then I have a minus 5, and then I have a 1 there, and then I have a plus 6. So the answer is a 0. So if we start with x, so x is equal to 1 is actually one of the solutions of this particular equation, which means that x minus 1, I'm taking this 1 to the other side, x minus 1 is one of the factors if we want to factorize that. So how do we move forward then? Of course, we said x minus 1 is the solution. So to use the long division to factorize that, we place a 1 outside, and then we take the coefficients of this particular expression here. So we have a 1, and then we have a minus 2, and then we have a minus 5, and then we have a positive 6. And then what else do we need to do? We take this 1, we drop it there, and then we say 1 times 1 is 1. So we place a 1 there, and then after having this 1, we say minus 2 plus 1 is a minus 1. So this minus 1 times that 1, we get a minus 1. Minus 5 plus minus 1 is a minus 6. And then we take this minus 6 and then we place it here. And then this minus 6, of course, is minus 6 times 1. And then we get a minus 6, so we place it here. And then we add 6 plus minus 6, which is a 0. Take note that if this x was not one of the solutions of this particular expression, one of this the solution of this equation, then here we're not going to have a 0, we're going to have some remainder, which means that in this case, since we have a 0, then x is equal to 1 is one of the solutions. What that's supposed to mean for us, it means we have x minus 1 as one of the factors, and then the other part is this part here. So this is gonna be 1x squared minus 1x minus a 6 is equal to a 0. Now, this we have 3 terms. Remember that if we divide this, let's say we divide this by that, of course the order of this polynomial is supposed to reduce by 1. So if we start at 2, we will end up with this this 6 here being a constant. So this is how you end up factorizing this nice thing here. Now again, can we factorize this? Again, we also look for the factors of minus 6. Factors of minus 6 is plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Of course, we're going to start with a 1. If I'm plugging in a 1 there, will I get a 0? I am talking only about this part. This is what I'm trying to factorize now. So I want to have a 1 squared minus a 1 minus a 6. So 1 is not one of the solutions of this middle part there. Let us try a minus 1. If let's say we have a minus 1 now, what will happen? A minus 1 is also not one of the solutions we're looking for. So we cut this, it's not one of them. Let's go to minus a 2, minus a 2. So if we go to minus a 2, we will end up having a 0. So here we end up having a minus a 2 as one of the solutions. So we have x is equal to minus a 2. In other words, x plus a 2, taking this minus 2 to the other side, is going to be a positive. So x plus 2 is one of the factors. So this is going to be x minus 1 and x plus a 2. And then we have something remaining here. Now, here we're going to use a method by inspection. We already have the factor. Now we want to find out what is here. Because here we have a and we know that this is a solution. So what you do is simple. You take this x squared divided by x, so you will end up having 1x, and then you go to the last term, minus 6 divided by positive 2, you get a minus 3, and that's it. You have factorized this part. Now this will either be equal to 0 if this part is equal to 0, which means x minus 2, because if this is equal to 0, 0 times anything is equal to 0 is equal to 0, or x plus 2 is equal to 0, because anything times 0 times something is still going to be 0, or if you have x minus 3 is equal to 0. So if this happens, if either this or that or that or all of them happens at once, then you will get a 0, which means that the values of x that actually giving us a 0 is x is equal to 1, or x is equal to a minus 2, or x is equal to a positive 3. Now we have this, we have that, we have that. This is the information we're getting from the numerator. Now let's go to the denominator. If you look at the denominator, right, note that when x minus 3 is equal to 0, the given equation is undefined. Right. Now, if it is undefined, then x cannot be equal to a 3. This cannot happen because we'll get an undefined. So this cannot happen because we're going to get an undefined. So our critical values is x is equal to 1, x is equal to minus 2, and x is equal to a 3. Now, once you have the critical values, you draw a nice number line. How many of them? We have 3. 1, 2, 3. So which one is the lowest? It's going to be minus 2. You have 1, you have a 3. And then you draw some holes here and some holes there. Remember that x cannot be equal to 3, which means we have undefined. So this one we're not going to shade no matter what the inequality sign is. And then these two can either be shaded or not shaded. Now, if we go back to our original equation inequality here, this we had less than or equal to. Or equal to means shade. So we can shade this part. We can shade this part, right? This we cannot shade because it's causing our equation to be undefined. Now, the next step is we want to check the sign. What is the sign in this region? What is the sign in this region? What is the sign in this region? What is the sign in that region? So we pick a number that is less than minus 2. Let me just say minus 3 here. We pick a number here that is between minus 2 and 1. So it's going to be minus 1. We pick it here. We pick a number that is between 1 and 3. I'm going to pick between minus 2 and 1. Let me just pick a 0. It's easy to work with a 0. And then here, let's pick between 1 and 3. We're going to pick a 2. And then here, we're going to pick a 4. We want to check the signs. What do we do with these numbers? We take these numbers and we plug them here to see whether we're getting a positive or a negative. Let me see here. So we're gonna have this cube and minus 2 x squared minus 5 x plus a 6 divided by x minus a 3. So you have this minus a 3. But if you look carefully to this, if you don't have a calculator, you can work these numbers out. I mean, if you have a calculator, you can work these numbers out, plugging them there. But if you don't have a calculator, there's an easier way for this. Remember that we said that this inequality is the same as x minus 1 and x plus 2 and x minus a 3 all over x minus 3. Remember that I don't want you to cancel this and that, because if you do that, you're losing some information. Right, we had this inequality. So if let's say I pick minus 3, if I plug in minus 3 here, I will get minus 3 minus 1, and I'll get minus 4. So I will end up getting a negative. If I plug in minus 3 here, I will get a minus 1, which is minus. If I plug in a minus 3 here, I will get a minus. If I plug in a minus 3, I'll get a minus 6, which is also a minus. Right. Now, if I have something of this type, minus times minus times minus, minus times minus is a positive, positive times minus a minus, minus divided by minus is a positive. So here the answer you have is, you have a positive there. Now, we want to plug in a 0 here. If I plug in a 0 here, I will get a minus 1, so we'll get a minus. If I plug in a 0 here, I will get a positive 2, so I'll get a positive answer. If I plug in a 0 here, I will get a minus. If I plug in a 0 here, I will get a minus. So minus times a positive is minus. Minus times a minus is positive. Positive divided by a minus is minus. So we have a minus sign there. Now, if I plug in a 2 here, it's going to be 2 minus 1 is 2, so we get a positive answer. If I plug in a 2 here, I will get 2 plus 2, which is a positive answer. If I plug in a 2 here, I will get a minus 1, which is a negative answer. If I plug in a 2 here, I will get a minus 1, which is a negative minus 1, which is a negative answer. So positive times positive, I get a positive. And positive times negative, I get a negative, and negative divided by negative, I get a positive. So here we end up having a positive. Now, what happens at 3? Remember that we have this 3 because we are hoping that when we have this part, we will end up having there is a possibility of a change in sign. That is why we usually have this. Now, if I pick in a 4, plug it here, what will I get? A 3, which is positive. 4 plus 2 is a 6, which is positive. 4 minus 1 minus 3 is a 1, which is positive. And here we're gonna get a positive. So in this particular region, you get a positive answer. Now, what is the region we are looking for here? So the region we are looking for here is this part of here, because we want it to be less than or equal to 0. So the correct answer is I want x to be less than or equal to 1. I also want minus 2 to be less than or equal to x. This is the desired answer we're looking for. Now, why are we having a plus and a plus here? It happened that this part actually is not changing the sign. Now, how will that look like? If we were to draw this, remember that this thing here is the same as x minus 1 and x plus 2. This function here is x, but x cannot be equal to a 3, because if x is equal to 3, this will be 0, and we don't want to have a 0 in the denominator because it's going to make it undefined. So to plot this graph, it was supposed to be a graph of this type, but now when x is equal to 3 here, we're supposed to have a hole there. So there is no change in sign. That's what is basically happening here. So the shape will look like this, but at x is equal to 3, you will end up having a hole. So that's all for the revision part of what we did Friday. But today, what I want us to look at is what is a function. What is a function? Now, in a matter of definition, a function is, let me just write this, maybe. A function is a rule that assigns each element in the set D to a unique element in the set E. That's what is a function. So basically we have two sets. One set is here, we call it D, and we have another set here, we call it E, right? Now, what a function is actually doing, it takes one element here and maps it to some element there. So one element have one output, and then I can maybe say this is just an x, and it also takes another element here, maybe we're gonna call it A, and it maps to some element there, right? And another element here may be a B, and then it assigns it to some element there, right? So the function is that rule that assigns an element here to an element there. Now, if all these, remember that each element here must be assigned to an element there. Getting it? If all these elements, we say that this D is called the domain of F. This is the domain of f. Right. If this set is containing all the possible image of what is there, this set is called the range of f. Right. Now that you have this nice thing here, let me explain again. If let's say here, remember the definition, it takes only one element here and maps it to an element there. So if let's say I have an elements here, I have 1, 2, 3, 4, and then here I have one element, let's say I have 10, 15, 17, let me say 19. Now if here I have this element is mapped to that, this element is mapped to that, this element is mapped to that, this element is not mapped to anything, and we have this relation f here which maps elements from this D to this E. Is this rule a function? Yes or no? The answer to this is that for this rule to be a function, it must map each element that is here to the element that is there. But if you pick this element 4 here, this 4 is not mapped to anything there. So this is not a function. Right. If this was a function, then D is not the domain of that, unless we can cut a piece of it and say, okay, if we are dealing with this piece here, we can say that, okay, in that particular case, f will be a function. Now, let's look at other several examples of this. If let's say you have a relation, this, let me say this is a D, and this one here is an E. And these are the objects that are here. I'm just gonna call them 1, 2, 3. And then here I have 10, 11, and 14. If each element here is mapped to one element there, and each element that is here is only an image of one element there, like 1 to 1, 1 to 1, there is no element here which is an image of two things that side. So we say that we taken one element here to one element there. So this is a 1-to-1 relation, right? And a 1-to-1 relation is a function. In that case, we have a function, 1-to-1 relation. But let's move on. If let's say you have a set of things 1, 2, 3, and then this side you have 10, 11, and 15, and you notice that this element here is mapped there, and the same element have also another output. So this input element here is mapped to two outputs there, but this one is only mapped to one element, and this one, let me redo this. Okay, let me do this part here. Let me put a 16 there. But this element here is mapped to one element, and this element is mapped to one element. You can notice this side that you have only one element that have more than one output. That side. Remember, this side is output, and this side is input. Input means domain, range, right? Now that you have that, there is only one element this side that have more than one output. So you have one element this side that have more than one output to many outputs. So this is one to many. Going back to the definition of a function, we want each element to have one output. Each element to have one output. So one to many is not a function, because there is this one element here, one input that have more than one output. So that is not a function. Now, another one will be you have a set of things here. We have a D, you have 1, you have 2, you have 3, and then this side you have 11, 10, 15, and 16. Let me put it like that. And now you have this is mapped there. You have this is mapped there. You have this is mapped there. Just making a simple example. And here, let me say you have 4, 5, and 6. Let me just say here you have that, and here you have that, and here you have that. Remember that this is our D, this is our E. This is a set of output values. This is a set of input values. So now that you have this D for domain, and this one is the range, domain this side. Now, if you look at each of these elements this side, you have these 3, 1 up to 3. They are mapped to one thing. You have many things this side mapped to one thing that side. So we have many to one. Many of these things mapped to one thing. So if you note on this side, the definition of a function, you look at this side. Each of these things must have one output. How many outputs does 1 have? It has one output. How many outputs does 2 have? It has one output. How many outputs does 3 have? It has one output. We don't have any of these elements having more than 2 outputs. So this one is a function. This is a many-to-one relation, which is a function. Right. Now, the last one is, suppose you have this set of things here, 1, 2, 3, 4, and then this side you have 10, 11, 12, let me just say maybe 13. Now, I still have a relation, but this relation here, I have this is going to 10, I also have this going to 11, I have 2 going to 10, I have 2 going to 12, I have 3 going to 13, I have 3 going to maybe 11, I have 4 maybe going to 1, it doesn't matter. But if you look at this side, I have many elements this side that have more than one output. If you look at one have 2 outputs. It can either have 10 or 11. So 1 have 2 outputs. If you look at 2 has 2 outputs, 3 have 2 outputs. So you have many elements this side that have more than one output. Right. Now, when you come to this side, you will find out that this one thing is mapped to so many things. So it's going to many outputs. So it's many to many relation. Right. So many to many relations, is it a function? Is it not a function? First, let's pick one element here. If you look at one have more than one output. A function wants each of the elements in the input. This is our input. This is also known as the domain. It wants to take each of the elements in the domain to have only one image or one output. But this one have 2, therefore not a function. This one is not a function. So those are the things that we actually usually talk about. So now, how do we know what is a domain? A domain of a function is a set of all input values that can be plugged in F, or is the set of all values X such that the function F is defined. That's a domain, the definition of a domain. Domain is the set of all input values X such that F of X is defined. Right, that's what is a domain. And the range is the set of all the possible outputs of F of X. That's simply as that. Now let's take some examples here. Suppose you have this example here. You have your f of x is equal to x plus a 1. Now we want to plot this, or even without plotting this, what will be the domain of this function? Remember that this function here doesn't have a root, doesn't have a power, doesn't have, it's not a special function, it's just a stupid polynomial. So this one here is defined everywhere. I can plug in any value here, positive or negative, this will be defined. So in this particular case, our domain is going to be the set of all real numbers x. That will be the domain of this function. We usually have this subscript to say this is the domain of f, but d is usually fine. Now if you look at this, or we can even plot it if you want, and if you plotting this, the normal function y is equal to x is usually passing through the origin like this, but now we have a 1, so we want to push this function 1 unit up, so it's gonna be of this type, so you are shifting it 1 unit up, so it's supposed to go like this, and here you're supposed to have a 1, right? So this is what it's supposed to look like. But if you look at this is gonna go up to positive infinite, this is going down to negative infinite, so it's taking all the values, it's defined everywhere. So our range E is going to be the set of all real numbers, y, set of all real numbers. So in this case we're still gonna have that. Now we talked about a one-to-one function, we talked about what is a range, we talked about what is a function. Of course we're still gonna talk about the range later on in the course, how to find the range, and we're still gonna take some examples of the domain. Now how to identify if you are given a table, how to identify if this table is that of a function, and how to identify if the curve is that of a function. I'm supposed to think of this. Suppose I have this nice table here. Remember that a table can either be of this type, which means you have 2 rows of this type. I'm just gonna make 2 examples here. You have this one here, and then I will do the graph, the curve, and then we talk about it, and then after that we take one exercise and then we can stop. Now this is the first one, and then I'm gonna have another one of this type. I'm gonna have another one of this type. I'm gonna have this, I'm gonna have that, 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 and then I'm gonna have that. And then what is important here, and then I'm gonna have 3 curves. This one is gonna be like this, and this one is gonna be like this. Okay, and then I'm gonna have another one here, and then I'm gonna have another one here, and then I'm gonna have another one here, and then I'm gonna have another one here. Let me add the last one, and then we take the exercises, 2 exercises, and then we can stop. So I'm gonna have this. So how are these curves gonna be? This one I want it to be of this type. Okay, this one I want it to be of this type. And now let me do this. This side we're gonna have y-axis, this is gonna be x-axis. Okay, and then this side, so you're gonna have a nice curve like this, and then here I want us to have a nice curve How about I draw a cardioid and see you have a nice curve like this. Nice curve like this. Yes. And then this one is of that type, and this one is of this type. These are the y-axis, these are the x-axis. This is going from negative infinity to positive infinity, but this side is y-axis, these are x-axis. Just for fun here, I'm just gonna place a 5. Suppose this value here is a 5. These are the x-axis. These are y-axis, these are the x-axis, and this one is going from negative infinity to positive infinity. Okay, now let's go and fill in the tables. This table here, I'm gonna place a 1, a 2, a 3, a 4, a 5, a 1, and a 1, 2, 3, 4, 5. Let me place here a 6. Here I'm gonna have a 10, 11, 1, 7, 2, 3, and 4. And then this side I will have a 1, 2, 3, 4, 5, 7, 10, 11, 12. And then this side I'm gonna have 2, 1, 3, 7, 3, 4, 1, 5, 7. These are just random numbers. Now, whenever you are reading a table of this type, you must know that the first row is always the set of input values, or the domain. The domain is always contained in the first row. And also here, the first column is always the set of input values, or is supposed to contain our domain. And then this one is the set of output values, and this one is the set of output values. So now we have this, we understand that. Now the question is this table that of a function? When you are checking if something is a function or not, you only focus on the input values. Forget about the output, you only focus on the input values. Now, if you look here, you have this input 1, it has an output 10, and you go down the line, you have this input 1, it has an output 3. So you have one number 1 that have two outputs, 10 and a 3. So because one input have two outputs, this is not that of a function. There's nothing else you have to check for. You only check the outputs if you are trying to find out if is it one-to-one, one-to-many, and all those things. And also for this one, if you look, it's only one that have many outputs. So also this is one to many relation. It's one to many relation, so it is not a function. But what about this one? If you look here, 1, there's only 1 this side. 2, there's only 1 2 here. 3, there's only 1 2 here, 3 here. All of these elements this side are unique. So each element have only one output, each element have only one output, each element have only one output. So if you look into this, you will find out that all these elements are different in the input column. So this one, because they are different, mapped to unique elements, so this one is a function. So that's how you actually read a table. It is a function. Now if you look into this, looking at 1 here, you have 1 is mapped to 2, okay, only. But if you look at 2, for instance, looking at 2 is mapped to 1. Where is another one? You have 1 there. So we have 2 mapped to 1, and we also have 10 mapped to 1. Again, if you look at 3 and 5, they are mapped to the same thing. So we have many things here mapped to one thing that side. You getting it? And also one thing that I also wanted to mention here, when you have many to many things, you will find out that in those particular many to one, if you have this, let's go back to this, I wanted to specify this, then we can go back. You have many things here that are mapped to many things. This is usually used a lot in data analysis. Just because something is not a function, it doesn't mean that it's not studied or it's not used. So people will be doing data analysis, they usually deal with many to many relations a lot. But here, for the sake of this example here, you will find out that if I look at these elements, there are many of these elements mapped to one thing, that side. So here you have many to 1, right? So this is a function. It's not many to many. Once we say many to many, it means that there is one thing here that is mapped to many things, and there is also another thing that is mapped to many things. So we have many things this side that are mapped to one thing. So this is what is basically happening. It is a function, right? How about the plot of curves? How do you answer the questions if a plot is that of a function? So you wanted to check if every time when you pick an input element along the x-axis, it has one element, it has one output out there. Every element, it has one output there. Every element, it has one output there. So the best way to do that is to create a vertical line, right? If you have a vertical line, you start from this side here, and then you keep pushing it. What is happening here? So you have this line here, and then you keep pushing it, moving this thing along this side, and see if how many times is it gonna cut this curve if you keep pushing it to this side. So if at all the points here the vertical line cuts the curve once, then it is a function. For this one, you can clearly see that this is a function. You use a vertical line test. A vertical line test, keep cutting the curve once up until you arrive to the end. So this is a function. But if you look into this nice heart here, what am I doing now? If I place a vertical line here, let's say here, I cut this heart like this. This curve is like this. You can see that it's gonna cut this curve here. It's gonna cut this curve there twice, more than once. So this one is not a function because the vertical line test cuts the curve 2 times. So this one is not a function. But if we look at this curve here, whenever I place a vertical line here, it's gonna cut the curve. This is the curve. It's gonna cut it once here, once there, once there, and once there. So this is also a function, right? Because it cuts once. But if you look at this one here, whenever I'm placing here vertical line here, yeah, it cuts it less than 2 times. But when you arrive here, if you place a line here, the vertical line here is gonna overlap here. So it cuts this here, it cuts it there, it cuts it there, it cuts it there, it cuts it there, it cuts there, it cuts there, it cuts there, it cuts. In fact, it cuts the curve infinitely many times. So if I place, let's say, a vertical line here, I'm trying to be precise as possible. So it's gonna cut this. So for this particular case, vertical line cuts the curve infinitely many times, so not a function. So the vertical line test fails to prove that this curve is a function. That is why most people find out that the vertical line test fails, but that's what this actually means. Now, the actual example that I wanted us to look at was cancel. Let me do this. So I wanted us to look at these problems. You can see that here, which of the following relation is a well-defined function? Is it a function? First of all, you just look at the input values. You have a 1, you have a 1, so, and these numbers are different. So this one is not a function. And then, because we don't want input values to be repeated, and then when it comes to this one, if you place a vertical line here, it's gonna cut the curve there, cuts the curve there, so it cuts it twice. So the vertical line test is saying that cutting this thing more than once, not a function. Right. Number C. When you are listing, this is a set of a coordinate system in a graph. So the first number here is always the x value, and then the second one is the y value. So if you look first at the x values, this is different from that, and this one is different from that, and this one is different from that. All of them are different. I don't care what the outputs are, but I know that input values are different. So this one is that of a function. And now when we come to this one, here is shaded. It means that when x is equal to 0, y is equal to 1. But also here is also shaded, which means that when x is equal to 0, y is equal to 0. So we have this one value here, which is equal to 0, being mapped to two different things, which means this one is just not a function, because we don't want to have one element mapped to two outputs. You have one element has two outputs, so not a function. Because this one is saying none of the above, and we know C is correct, so this is not correct. So C is the correct answer. Now we can go to number 7. But if you look here we have a hole. Because we have a hole here, which means that along this side, the function here is not defined. So there is no value here. It is only defined here. So in this case, this function here, when x is equal to 0, we know that y is equal to 0. We cannot take that because there is not defined. It is only defined here. So here the function have only one. It has only one value. So this one here is a function. Just I wanted to clarify that because of the dot, and this is empty hole, this one is a filled hole. Now, but the question here is asking which of the following relation is a one-to-one. Now, how do you determine if a function is a one-to-one? So you wanted to make sure that if you have inputs, different inputs have different outputs. But for this case here, if you place a horizontal line here, you will find out that this value here is the same as that value, which is the same as that. But if you look down here, this input element is not the same as that. So we have many here, we have many elements mapped to one thing, which is that value there. So it's many to one. It's not a one-to-one. This is not a one-to-one. And then if you look at B, you have 1 to 5, we have 7 to 8, we have 2 to 5. So if you look at this part, 1 is mapped to 5. Look into this part, we have 2 is mapped to 5. So we have this is mapped to 5, and then if this is mapped to 5, so we still have many to 1, because this and that and that and that are different. So again, we have many to 1 here, not a 1 to 1, still out. And if you look into this, if you place a vertical line test here, you can see that whenever I have this element here, it's gonna cast the curve there and there. So we have one element here. This one element, you have one element here which is mapped to 2 things, and if I pick another element, it's mapped to that and that. So we have more than one element, many elements mapped to many outputs. So this is many to 1, not a 1 to 1. This is not the 1. Now let's go to D. D, we have 3, 4, 2, 5, 7. First of all, these are all different. So this is a table of a function. Now we want to look at the outputs. Are they all the same, or are they all different? Now, if you look into this, you have a 4 here, you have a 4 there. So 5 is mapped to 4. 3 is mapped to 4, and 5 is mapped to 4. So we have 2 numbers that are mapped to one thing. So we have many to 1 again here. Many to 1. So this one is a function many to 1, but it is not a 1 to 1. Remember that here we're looking for a 1 to 1 relation. So this one cannot be it, this one cannot be it, this one cannot be it. And looking here, we have this output and that output belonging to 2 different things. It's not it, which means the correct answer here is supposed to be an E. And that's all we actually have for today. We're gonna stop there.